Hi, this is Christina from DNVGL. I will start by giving you a short introduction to the Open Simulation Platform, or OSP for short. I'll then hand over to Kevin from SINTEF Ocean, who, based on this platform, has developed a tool for design of maritime hybrid systems. Our vision is to enable collaborative digital twin simulations to solve challenges within designing, commissioning, operating, and assuring complex integrated systems. Meaning systems where multiple suppliers deliver components, sensors, and software that shall work together, and where we consider simulation models an important part of the virtual documentation that shall follow a vessel from design phase and into operation. First, let's look at a typical vessel lifecycle, where the red mark points at how integration tests are typically done towards the end of the construction phase. This is when suppliers have delivered their systems to the yard and have connected them on board. At this stage, there is actually minimal room for changes in the design, and only a limited set of system functions can be tested, both due to time constraints and to the feasibility of testing. With the OSP, we would like to enable the industry to shift left by performing virtual system integration, commissioning, and testing before the physical vessel is built, thus saving time and reducing risks during both commissioning and in-sea trials. An up-to-date simulation model can then follow the real vessel into operation, also enabling a range of use cases such as change management, training, and planning of complex operations. This project is not only SINTEF and DNVGL, but was started in 2017 together with Kongsberg Maritime and NTNU. And we have decided together to establish a joint industry project to confirm that the ideas behind the platform was supported by the maritime industry. And the list here shows the support from a wide range of such stakeholders. And the main development in the project has been done by the initiating partners, but with valuable input from the JIP, for example, in the use cases as Kevin will show from his presentation later. We all know that simulation is a core technology when designing, optimizing, and operating new assets. And specialized tools and methods for modeling and simulation are many, but they are typically not made available for collaboration and reuse as we want them. And to best make use of these investments and assets, we need a unifying approach to enable digital collaboration across these disciplines and sectors. Next slide shows one such approach, and that is co-simulation. It allows to cobble independent standalone simulation models, including also their numerical solvers, to establish full system simulations. And is well suited when the sub-simulators span a range of physical domains. And that is why co-simulation is the approach we have taken in the OSP project. We want to make use of the simulation models developed by suppliers in their preferred tools to create larger system simulations without revealing proprietary information. For this, we adapted the use of the Functional Mockup Interface Standard, or FMI for short. This is a widely supported tool-independent standard for making submodels compatible with each other in a co-simulation context. And from a simulation tool, you can then export your models as shown here as a functional mockup unit that can be used with any tool for co-simulation supported by FMI. And note that the FMU is illustrated in black here, and it indicates that in the process of exporting the model, it's compiled to binary code and therefore appears as a black box model to anyone who wants to use it. And using this existing standard, we have come a long way in achieving model reuse and IP protection, which are key elements for sharing simulation models with the OSP. This slide illustrates three partners that needs to collaborate on simulation, making their models from their domain available as FMUs. FMI provides compatibility at a low level, but it does not provide higher level information about what the simulation variables mean or how to set up the model interconnections. Addressing this, we have developed the OSP interface specifications to more efficiently configure such setups. And for OSP, we have also developed the software that orchestrates the co-simulation, meaning that it handles time synchronization and communication between simulation models. In addition to achieving this or to driving the simulations, the OSP software includes several important features, and some of these Kevin will explore in his use case later. Most important being that it's open source and free to use for all. And in order to drive standardization, ensure interoperability and between stakeholders and tools, and enable common working processes, we believe that this common open source software for co-simulation is the key. And next is a slide of the OSP project page, where all results from the joint industry project is shared, including links to GitHub for models and source code, and more on the background of the project if you'd like to read about that. And our goal is that the open source software, specification, and example configuration shared here will form the basis of an active open source community around this platform. That industry in general, in their development and in collaboration with academia and R&D, will benefit from using this platform and software and contribute to a joint development. With this, I hand the camera to Kevin to tell you about how he has used OSP to establish a tool for the design of maritime hybrid systems. Thank you.
Thank you, Kristine. Hello, my name is Kevin Kusop-Yum. I work as a research scientist in SINTEF Ocean in Trondheim in the area of design, simulation, and testing of hybrid power system for maritime industry. I also led one of the 3 use cases in the JIP project. In the use case, the main question we tried to answer was if co-simulation using OSP software is a useful tool for the system design in early stage. The question is, in short, can we or should we run a system simulation using OSP from day one? So we formulated the use case into a collaborative design study together with partners in the JIP. The main goal of the design study is to explore the design space of the hybrid power system together with control parameters that give minimum fuel consumption within allowed drop-off state of charge. Why did we select this use case? We wanted to explore the feasibility and benefit of using OSP in the early design stage, where you need to run a large number of simulations, build a system model with the components from different parties, and apply model-based systems engineering and knowledge-based engineering. Why do you need dynamic system simulation so early? In the hybrid system, a battery or energy storage device unlocks the possibility of optimizing the design or operation by easing the requirement for the power balance between the consumers and producers. Peak shaving, load leveling, spinning reserve, zero emission mode are such operations. A challenge is that these operations will not always save energy, but may be opposite. A proper control strategy with correctly sized machinery under specific operation profile will maximize the benefit of the novel technology. Here, the system performance is of our key interest rather than best performing components. In addition, we need to take into account the dynamic property of components, primarily battery, to evaluate the system performance. When to charge or discharge or how fast, all this combined will result in a better or worse performance. OSP, as a co-simulation software, provides a platform where we can create a system model in collaboration, without concern of breaching IPR. As we work with models on the platform, we can communicate our requirements, specifications, and interfaces through models and get more tangible feedbacks and evaluation. Finally, as it is an open source software, it is up to the developer to customize the tool to the specific needs as we have done in our use case. We selected the target vessel and system as shown here. It is a road ferry designed by Damen Shipyard. You see the schematic single line diagram on the right. The hybrid power system has two gensets, which are LNG fueled, and the two propulsion motors fore and aft each. Two battery packs are connected to this grid on each switchboard. Here's the operation profile of the ferry. The ferry will transit from one terminal to another with a fixed speed reference at 12 knots. The left plot shows the actual speed simulated during the acceleration phase and transit. On the right, you can see that there is a short period of burst in power for the acceleration. It gives an idea that peak shaving strategy can be effective for downsizing the power sources and reducing fuel consumption. For more efficient design and operation, we wanted to look at two control strategies. The first one applies when the power load is low, typically when the ferry stays in terminals or decelerates toward the terminal. In this mode, the batteries will supply the total power load if its state of charge is above a low limit, while gensets are turned off. The other mode applies to high power profile. When the load is above a upper limit, a battery will cover the power above the limit, so-called peak shaving. When the power load is between these two limits, battery will be charged by the genset. Here's a typical simulated system response for a hybrid power system with these strategies in place. Here you see that the battery is responsible for the propulsion and auxiliary load in the beginning until the gensets are ready for providing power. In addition, there is a short power rush to accelerate the vessel, so peak shaving is happening. As the propulsion load is going down to a steady state, a battery is charged in order to maintain its state of charge. When the state of charge is at a desired level, charging stops and all powers are supplied by gensets only. At the end of the journey, propulsion load drops and the vessel is on zero emission mode. There are lots of things happening in this short transit, and it will be very difficult to tell whether this type of operation will really save fuel and reduce emissions at reasonable capital costs without running the dynamic simulation. We spent some time together in the team defining the system scope, structure, and model fidelity and interfaces. These were crucial steps before we go down into modeling activity. FMU models are actually developed by 5 participants and delivered to me so that the system can be configured. As we needed to run a large number of simulations, we mostly used quasi-steady state models, while maintaining a crucial dynamic property such as vessel motion, propulsion, load changes, and power balance in the power system. The system simulation typically runs at 30 or 40 times faster than real time, which is ideal for the early design stage trials. This system model can be further elaborated in the later stage while keeping its structure to serve other needs such as design evaluation, verification, hardware in the loop testing, and virtual commissioning. Then we have selected the main design parameters that will affect the fuel consumption and state of charge of the battery. These are rated power for auxiliary engines, upper limit for peak shaving, lower limit for zero emission mode, and battery capacity. We sampled about 100 cases for each battery capacity using design of experiments, specifically using Sobel sequence method. Another main task in the use case was to develop an integrated design tool that embraces the design process with an intuitive user interface and support for database. In order for the tool to be a collaborative tool, the tool is developed as a web application where many users can work simultaneously with the same source of FMU models or system models. We followed these work processes to complete a design study. When we collected all the FMUs from the partners, we uploaded FMU to the server and defined interface using OSP interface specification to simplify the connections. Then we move on to system configuration, where we select FMU components to be included from the database, connect FMUs, and define initial values. Next step is to configure the simulation setup. Here we need to define scenarios for and design cases. Optionally, we can define logging configuration to specify the variables to be saved, and then run simulation. After simulation of multiple design cases is complete, we observe the summary and download the result for further post-processing. Let's look at snapshots of the tool. You can also follow the link on the slide to see the demonstration on YouTube. This is the starting page of the application. As mentioned, you can open this application by giving a proper address for the UI server in any modern web browser. This is the page where you can upload FMUs to the server. After you upload it, you can see the information of the model, such as parameters, inputs, and outputs. You can put additional information such as category to sort FMUs for later use. When the FMUs are collected in the server, you can open the system configuration page. Here you can drag and drop an FMU from the left pane to the editor session. On the right pane, you can see the detail of the component selected. Here you can add interfaces to be connected and add initial values for the component. When the system is configured, you can run simulation. Before that, we need to set up our scenario for the system simulation to run with. For the design study, we created design variables and defined its range so that a set of design variables can be sampled using a design of experiment method selected. Then we can run simulation. When the simulation is complete for all cases, we can see the summary table that gives the main output, which is state of charge at the end of journey and fuel consumption. We can download this table for the post-processing of the result. Let's look at the simulation result and see what we can learn from this about the system. The main outputs of the interest are fuel consumption and state of charge drop over a single trip of 1,300 seconds. We'll first look at the correlation between each design variables and the main outputs. We see that there are strong linear correlation between the rated power of gensets and both main outputs, whereas the correlation between the control parameters and the outputs are very weak. Initial conclusion from this result is that it is very difficult to draw any solid, simple rule of thumbs for the design. Let's look at this Pareto front plot, as two main and outputs are inversely proportionally related. We didn't pinpoint that the best design from this plot, but we have a very good idea how the fuel consumption will change for the given battery pack capacity and the given limitation of state of charge drop per trip. When the requirements become more solid, we can look for candidates for the best design from this plot. Concluding the presentation, I'd like to revisit the value of OSP in the design phase. In order to create a system model at this early stage, a collaboration work is important. OSP provides a means to share models and communicate through the models. It doesn't require a special simulation tool for multi-domain simulation. Simplified interface enhances the readability of the system model and reduces errors. We also saw that as an open source software, it could be integrated to a fit to purpose tool for specific needs. However, there are also challenges. Debugging the system model is not so easy when there are errors in the simulation or outputs don't make sense. It will be helpful if we are assured that the models shared by others are trustworthy. We need a framework for testing the model to verify models and document the model for its validity. This is the end of our presentation. Thank you for listening.